Hi everyone, the topic of my talk is on cosmic filaments, dark halos and rotation curves. As all of you know, more than 3/4 of matter in our universe is comprised of some unknown substance, which does not interact electromagnetically and is known as dark matter. Historically, one of the key pieces of evidence in favor of dark matter was the flattening of rotation curves. Namely, if we plot the rotation velocities of different objects in galaxies as a function of the distance from the center of the galaxy, then from the distributions of visible matter, it would be the velocities would be expected to decay at large distances. However, what was actually observed in many galaxies is the flattening of velocities at large distances, implying the presence of additional gravitating but non-luminous mass. One can conjecture that this flattening can be produced by a quasi-logarithmic gravitational potential. A simple geometric intuition from electrostatics tells us that quasi-logarithmic potentials can be produced by elongated mass distributions, and here we have two options. Either the dark halo itself is elongated in the direction orthogonal to the galaxy plane, or there is a long and thin string-like object in the center of the galaxy. For the purposes of our analysis, we have worked with two commonly chosen dark matter profiles, the Navarro-Frank-White profile and the Burkhardt profile. And as you can see from these graphs, if one deforms the profiles, then the rotation curves would yield steeper rises and shallower declines at large distances, for both the Navarro-Frank-White profile and the Burkhardt profile. But according to qualitative analysis of galaxies from the spark sample, the improvement in field quality is actually marginal at best. For example, for the two galaxies NGC 5371 and NGC 5907, you can see that if we take the deformation to be physically plausible, like no more with the axis ratio no more than 2 or 3, one can see only a slight improvement in fit quality. Nonetheless, if instead we opt for an elongated filament at the center of the galaxy, it can produce considerable improvement, larger than 50% for a number of galaxies. Here you can see, for example, for the NGC 5371, one can notice, especially for small radii, this non-zero velocity values are not expected to be reproducible by dark matter profiles. At least it's difficult, because the dark matter contributions tend to decay at small radii. However, they can be naturally reproduced with a string-like object at the origin. You can see the same for NGC 5907, and you can also see improvement in accommodating the flattening of the rotation curve at large distances. Now the question is, if these filaments at the center of galaxies do really exist, what could they be? First of all, they may be interpreted as astrophysical objects like tidal streams. For example, in JC 5907 is known to host a tidal stream, or polar rings, as is the case for another galaxy. Then they could be jets of relativistic particles produced by the magnetic fields in the vicinity of a black hole, or spaghettified matter distributions. Since the spaghettification effect is gravitational in nature, it could be the spaghettified filaments could be made of either baryonic or dark matter. Then it could be conjectured that they could be related to the larger intergalactic filaments. It would be possible if the galaxies in question lie at the nodes of intergalactic filamentary network, the large-scale structure. And finally, one should consider the more exotic possibility, the cosmic strings. It has been predicted by theorists that that if cosmic strings formed in the early universe, they are expected to migrate to the centers of galaxies. One filament type object was also observed at the center of our own galaxy, the Milky Way. It has been interpreted as either a black hole, jet, or a cosmic string. Then we have the nanograph results. The recent results are published. The recent interpretation published in around September last year, according to which the results of pulsar timing observations could be related to gravitational waves produced by cosmic strings. I should also note that the filament tensions in our fits are below the upper bound from Planck, which means that while this conjecture is still speculative, it's not an impossibility. Finally, I'm moving on to conclusions. We have observed out of the 82 galaxies from the Spark database that we have analyzed, we have obtained considerable evidence for the presence of an elongated object at the origin for about from 5 to 15 galaxies, and on the contrary, dark matter halo shape does not appear to have a significant imprint on the rotation curve. We also know that performing the same analysis for different dark matter profiles can be a powerful tool for detecting model independent, some very generic geometric model independent features. So if it's present for one dark matter profile and for another dark matter profile, then one can conclude that this feature is somehow model independent. We also expect that the gravitational lensing observations produced by Euclid, which the data on it will be available in several years, will allow us to shed more light on these important issues. Thanks for your attention.